Greetings of the day. Welcome back to our lecture series on the course Material Science and Metallurgy. So in today's session we will discuss in detail about point and line defects in the solids. Here I'll show you the overview of today's presentation. So we will recall what we have discussed in the last class, that is introduction to the crystal defects. Then we will, in particular, in today's session, we will discuss more about point defects and line defects. Under the point defects, we will discuss vacancy defect, interstitial, substitutional, Frenkel and Schottky defects. Then in the line defects, we will discuss dislocations mainly, the edge and screw dislocations we will discuss, and finally we will summarize. So as we have discussed last class, there is no solid material which is perfectly structured. That means every solid consists of a certain degree of defects that are present in the material. So defects can be present at the atomic level. These defects influences the properties such as strength, conductivity, or the durability of the material. So it is very much important to understand the behavior of these defects. So as we have seen in the last class, the types of defects are being classified according to the dimensionality. So first one is point defects, which are basically effects at the individual atom level defects, point level, or the zero dimensional defect, which is also called as. Then we have line defects. Majorly it's a row of atoms that are missing in the crystal lattice, then along a particular line or the length. So those defects are called as line defects, and they are also called as dislocations. And these are the one-dimensional defects. Then we have the surface defects, that is grain boundaries, which are the two-dimensional defects, which varies with the two-dimensional defects. Grain boundary misalignments are considered under the surface defects. Then we have the volume. Three-dimensional defects are considered as the volume defects. That includes the cracks and voids and certain inclusions. So these are classified, these are the defects that are classified based on the dimensionality. So this is basically based on the dimensionality. Okay, this is zero dimensional, this is 0D, and this is 1D, and this is 2D, and this is 3D, three-dimensional defects. Okay, so in today's lecture we will discuss more about point defects. So point defects are also considered the defects that are present at the atom level. So in definition, we can say point defects occur when individual atoms are either they are individual atoms, either they are missing or misplaced, or they were being added within the crystal structure. Okay, as we have discussed, at the point level, individual atom level defect, it's also called as atom level defects, whether they are missing, as we have seen, as you can able to see in the picture. So as you can see here, so you can able to notice there is a missing atom here in this particular region, and the misplacement of atoms is also can be observed. So misplacement of atoms can be observed over this region. So if any kind of misplacement or missing or an additional atom has been added to the crystal structure, such defects are called as point defects. So point defects are further classified into majorly of three categories. That is vacancy defects. Basically they are the missing atoms causes the weakness. Missing atoms are considered as a vacancies. Vacancy is an empty region wherever the atom is been missing. So those areas in the crystal lattice, it creates a vacant region. So the missing atoms causes a vacant region, and so the defect is called as a vacancy defect, which basically causes weakness in the material property. Then we have the interstitial defects. Interstitial defects are you have perfectly arranged regular arrangement atoms, something like this. And in this regular arrangement of atom positions, if at all any interstitial in between the spaces of these atoms, if any additional atom has been considered, so such kind of positions are called as the interstitial sites. So if an atom has been added here, the extra atoms that is disrupting the structure and adding between the spaces of regular atoms, so those defects are called as interstitial defect. Then substitutional. So in the place of the original atoms are being removed, and in the place of that an additional atom has been. So in the place of this atom, an additional atom has been a different atom has been occupying the regular positions of the atom. So such kind of defects are called as substitutional. In the place of one regular atom, so another atom will be situating in that position. So these are called as substitutional defects. So in the last class we have discussed about the Titanic ship, the failure. So in that we have discussed the atom level Titanic steel material, the material that is being used in the Titanic ship. The steel is identified with high amount of sulfur content. So this addition of extra atoms, the sulfur atoms, basically these are considered to be the point defects. They are carefully been considered, but however the portion of the content is observed to be more, and which caused the reducing in the toughness, and so it reduces its impact strength as well, right? So in detail, if we discuss, so vacancy defects is, in short, we can call it as an atom that is missing from its expected position in the regular arrangement of atoms. If an atom has been missed, something like this in the image, if the regular atom, one of the atom has been missing in this portion, so this is basically a vacant region. So this vacant region, and so that is called as a vacancy defect. Okay. So these are basically vacancy defects are basically common in the metals and ceramics due to the atomic diffusion, the movement of the atoms, the diffusion, atomic diffusion. So what causes this? What is the effect of these vacancy defect? So if you look at, so it lowers the density, because as the atoms are missing in the material, so it reduces when you compare with the full arrangement, regular perfect arrangement of atoms, and the material that is having the vacancy of atoms. If you consider both, you can observe to be which is having the lower density because of the loss of atoms. And it is also lowers the mechanical strength, as some of the atoms are being missed or missing, and their resistance against the applied loads will also be lost, and so the mechanical strength is also being influenced or affected, right? And it enhances the diffusion properties, and which is helpful in making the alloys. It enhances the diffusion properties because the movement of atoms will become easier, because wherever we observe a vacant region or empty region, so the movement of the atoms can be easier, and so it enhances the diffusion properties, and that is somehow it is helpful in making the alloys. If I quote an example for this, high temperature steel degradation due to increased vacancy movement. So the high temperature steel, the degradation causes because of the increased vacancy movement, right? So this is one of the example for vacancy defect and its effect of the vacancy defect. High temperature steel that degrades due to increased vacancy movement. Okay. So next, when we come to the interstitial defect, that is an extra atom that is squeezed into the lattice structure. So you have in this region, if you look at closely, so in this region, the regular arrangement of atoms can be seen, the blue colored and yellow colored atoms, the regular arrangement of atoms can be seen, and wherever the gaps are there, these are called as interstitial sites. If in these interstitial sites, an atom has been located, so this kind of defects are called as interstitial defect. This is an interstitial defect. interstitial defect. Okay. Yeah. So the additional atom that has been situating in that has been squeezed into the regular arrangement of atom, that is considered to be an interstitial defect. So the presence of these defects causes increase in the internal stresses, because additional extra atom has been located between the regular arrangement of atom, and that causes certain stress in the material, in the atoms basically, and which causes basically the distortion of lattice, right? This is one of the effect. But it enhances the hardness and strength of the material, because additional atoms are being present in the situated in the regular arrangement of atom. So this also participates in the load bearing, the applied load. Okay, it offers resistance against the applied loads, and so the hardness and strength of the material will be enhancing because of the presence of these interstitial defects. One example that can be considered as a steel is a material. Steel is a combination of iron and the carbon. So you have iron, regular arrangement of iron. So in the regular arrangement of iron, carbon has been considered. So carbon will be situating in these interstitial sites. So carbon atoms in the iron forms the steel that basically improves the hardness. That depends on the concentration of the carbon, and we will be seeing that in our upcoming classes. So these kind of defect is called as interstitial defect. Then we have the substitutional defects. Substitutional defects are related to the atom replacement. So instead of having a regular arrangement, so one of the atom has been replaced by another. One of the atom in the crystal that has been replaced by the another atom, and that kind of defect is called as a substitutional. So in this example, you can see closely. So you don't have it in this position. Instead of having a blue colored atom, if you see the regular arrangement, so blue, yellow, and it is to be blue atom need to come, but another atom, the blue atom has been replaced with the orange colored atom. So this is basically substituting in the place of blue colored atom. So such kind of defects are called as substitutional defects. Okay, so what is the effect of the substitutional defects that are present in the material? So basically it alters the mechanical strength, obviously, and the conductivity of the material. It forms useful alloys like stainless steel and brass. These are formed because of the substitutional solid solutions. Okay. So if I take the example, in the case of brass is a combination of copper and the zinc. So in the copper, zinc is being added. So zinc atom will replace the copper atoms in the brass, and basically that improves the hardness of the material. So some of the copper atoms are being replaced with the zinc atoms, and that improves the hardness of the material. Right. So in addition to these interstitial and substitutional and vacancy defects, we do have another two types of defects that are basically identified in the ionic crystals. So in the ionic crystals, if it is observed with a pair of one cation and one anion can be missed from anionic place, and the pair of vacant ion sites are called as a Schottky imperfection. So as shown in the example, so if I consider this is a cation and this is an anion, so anion here is a missing of a cation can be observed. So in this case, a missing of anion can be observed. So these a pair of anion vacancy and the cation vacancy, a pair of vacant ion sites are considered to be the Schottky imperfection. So these imperfections are observed in the ionic crystals. And in addition to that, we do have another type of defects, that is a Frenkel defect. Frenkel defect is ion displaced from the lattice site into an interstitial site is called as Frenkel defect. So as a result of that, what is ion? If you look at closely here, so the anion present here that is being replaced and situating in an interstitial site. So this kind of displacement, and this what it causes It causes an anionic vacancy. A vacancy has been created, and also an interstitial defect has been considered. A vacancy, a pair of vacancy and interstitial defect, that is considered as a Frenkel defect. So we have Schottky defect, that is the pair of cation and anionic vacancies, that is called as Schottky defect. And we have a pair of vacancy and the interstitial site, vacancy and interstitial site, that is causing from one type of ion. So it could be cation or anion. So that pair of vacancy and interstitial defect, that is called as Frenkel defect. So next, going into the line defects. So what is a line defect first of all? So line defects occur when there is a continuous misalignment of atoms along a row in a crystal. So a group of atoms together in a particular direction along a particular length or along a particular line, if they are identified to be missing, so such kind of defects are considered as line defects, and these are one-dimensional defects along a particular line or along a particular length. So atoms are being missing. That is, in practical scenario, you can observe it in the cone. So in the cone, the regular arrangement of cone Frenkels, you can take it. So there is a misplacement of or missing pair. So you have these two lines and an extra line has been present, and that is stopped somewhere here, right? So this kind of defects we call it as a line defect. So in this line, the pair of missing atoms are there here. This entire line is being stopped here. So that means the missing of atoms are being present. So in practical scenario, line defect can be compared with this cone. So as a result of that, what it is causing? So it is an extra plane of atoms are being considered. An extra plane of atoms are being identified in the line defects. So this extra plane of atom causes a line defects. These line defects have been, this is also called as a dislocation. So these are classified into two types of dislocations. One is an edge dislocation, which causes an extra half plane of atoms. As discussed, this is an extra half plane of atoms. In this case, this is an extra half plane of atoms. So it is called as edge dislocation. Then we have screw dislocation. So screw dislocations are basically from atoms are arranged in the spiral pattern. So in the spiral pattern, as a spiral direction, atoms have been rearranged or arranged. So such kind of defect is called as a screw dislocation. So here, unlike the point defects, these line defects affects the whole row of atoms, which influencing the which basically influences how material bend and break. So the ductility of the material that will be influenced majorly by these line defects instead of point defects. Point defects are restricted to the individual atoms, and line defects are the whole row of atoms along a particular length or along a particular direction. You are having the atoms that have been misplaced or dislocated. So this greatly influences how the material will bend as well as break. In the case of titanic steel, so titanic steel lacked this ductility because of high presence of sulfur content, and that reduces the ductility and induces the brittleness, and which couldn't absorb the impact strength caused by the impact of iceberg ship interacting with the iceberg. So that causes huge impact stress, and that because of that impact strength, the material couldn't absorb it completely, and so it has seen a catastrophic failure. If we discuss more about this edge dislocation, the additional extra half a plane. So it is a row of atoms misaligned, forming an extra half plane. So that causes the edge dislocation. So what are the effects if edge dislocation is identified in the material? So it allows plastic deformation of the material. So we require plastic deformation instead of a brittle deformation. So plastic deformation is very much required, and that is good for the material. So defects are not bad. Defects are also good in some point of view. But we need to control the defects we have to understand it clearly, its behavior clearly. And it also causes localized stress concentration. Localized stress concentration also it causes. If you look at an example, edge dislocations in aluminum allows it to bend instead of breaking. So aluminum is known for its ductility, so it behaves very good ductility. So instead of breaking, the material tend to bend more because of the presence of edge dislocations in the material. Then if you look at screw dislocation, it's basically atomic level spiral misalignment. Atoms shift in a spiral pattern like a screw thread. The way how screw thread moves in the forward, clockwise and anti-clockwise direction, forward and backward movement. So in the similar way, atoms will be shifted in the spiral pattern. If you look at it closely here, you can see the shear stress that is being applied over this, and the way how atoms are being shifting along a particular axis, along a particular line. So this is called as a spiral pattern, the misalignment in the spiral pattern. Okay. So if this has been observed, and the screw dislocations have been observed in the material, it greatly influences how materials will crack and break. Okay. Then it is very critical in plastic deformation and the slipping of the material. Okay. In these two cases, greatly it influences the screw dislocation. One in the cracks and one in the plastic deformation and slipping of the material. If I look at the example, a high tensile steel uses screw dislocations for the strength, for strengthening, for improving the strength. So these high tensile steels will be using these screw dislocations carefully and in controlled manner, so that the strength can be tailored. So as a brief, if we compare point and line defects along a particular features, over a particular features. So if you look at the scale, point defects are very much to the atom level or the individual atoms level, and line defects are again the atom level, but these are basically a row of atoms, a series or group of atoms. Its effect on the strength, if you look at it, so point defects causes weakness and also it can strengthens, but the line defects usually weakens the material. What it causes, point defects are caused due to missing or an extra atom. So if an extra atom has been added into the lattice or a missing atom has been observed, so in both the cases these point defects have been created. And the line defects are caused due to the atomic misalignment. Example, if you look at impurities that are present in the steel, for the case of Titanic, we have seen Titanic steel consists of sulfur, high amount of sulfur. That is an impurity. It's a point level defect. And dislocations that are observed in the aluminum are the best example for line defects. And what is the industrial impact? So because of these point defects, industrially we can able to prepare the alloys, different alloys, and in the semiconductor industry also for doping the silicon with other metals or non-metals. So for improving the performances, these are greatly useful. It is having good industrial impact. And in the line defects, for work hardening is a technique that has been employed for improving the strength of the material, and in that particular case these dislocation defects have been helpful. So overall, if we summarize, before summarizing, so if you look at how engineers have been using these defects, so in the place of heat treatment process, for annealing also, for reducing the unwanted defects, engineers have been using controlling. For preparing the alloys, for introducing controlled defects for improving the strength, engineers have been using. And for welding and in the segment of welding and manufacturing, to prevent the weaker joints, engineers are using these defects. In the case of semiconductors, controlled defects have been created for improving the device performance. So these defects are intentionally or unintentionally is being identified in the material. So intentionally we do add the additional atoms into the material and for the better performance of the materials. So understanding the defects lets engineers design stronger, safer and more efficient materials. So understanding about these defects is very, very important. Overall, if we summarize, point defects impacts individual atoms, affects density and strength overall, and line defects influences materials deformation and mechanical properties. So understanding these defects helps the engineers design stronger and more efficient materials. So we will conclude today's lecture with this quote: defects are not always bad, they are crucial in materials engineering. So understanding about these defects is a key here. So with that note, we will conclude today's lecture, and in the tomorrow's lecture we will see more about surface and volume defects. So these are some of the references that has been used in preparing the slides. Thank you.